So it's actually a pleasure being here, even though the moment is not. We are remembering Gaspar, and that is a little bit sad to see that he's not with us any longer. This is a slide I used very often, in the sense because I like it. It's basically morphing of the CMS detector into a 16th century map, which has actually the reason why I'm using it here, because it has one thing which is in Italian, which is verso nuovo mondo, meaning exploring new world, exploring more. And I think this actually is one phrase which reminds me of Gaspar, because we have also been discussing with him since ever what to do next, what to do in the future, and he always had new ideas. And I think he basically has been, you have seen it in Portugal, that he has basically brought Portugal to the level it is today when it comes to energy physics. Now, as Gigi pointed out, it's not going to be trivial to achieve all of this great physics. And I'm going more to cover the challenges, some of the challenges on the experimental side. I know better CMS, and so I feel inadequate to cover fully what is happening in Atlas. But believe me, the challenges are on both sides. But I will be using mostly CMS examples. Okay. So here is a timeline of what CERN has been planning, and is basically the decision in 2012 to basically fully exploit the LHC led to this very detailed plan. And you can see that now we are in the middle of a long shutdown, which will implement the first set of upgrades of the accelerator sectors at CERN. But the real challenges will come only in 2024-2025, when the full upgrade of the accelerator system at CERN, and in particular the LHC, will be implemented. You can see here, I mean, Gigi pointed out the amazing performance of the machine, but really, I think that when we started, we would never have thought that we could even consider going to collect 3,000 inverse femtobarn. And here it's a little bit the challenges. I mean, it was already mentioned that at high luminosity LHC, we are basically dealing with, we are going to deal with two 10 to 35 luminosity level, and sorry, 2 10 to 34. And this is a mistake there. Now, the real challenge of this basically comes from the fact that if you look at how events look like today, this is how, on the left, you can see that is what we designed for our detectors. And we basically have been able to bring the performance of our detector to deal with what we are having today, which is pile-up, I mean concurrent proton-proton collisions, up to 40, 50 in average. But this we know we can handle, and we know we can basically get the kind of performance from the physics point of view, which we have seen today, which has led, for example, to the discovery of the Higgs boson even 2 years before than we had anticipated. So our software and our detectors have been doing much better than we had anticipated when we were designing it. On the other hand, it is clear that we will not be able to perform when we go to a situation where we will have 4 times more pile-up, I mean 4 times more concurrent reactions, which is what is going to be the situation with high luminosity LHC. In fact, the challenge is very practical. Let me give you a few numbers. High luminosity LHC to 10 to the 34 stable luminosity through the field basically means that our detector, part of our detectors will have to withstand 10 to the 16 Newton equivalent per centimeter square by the end of the exploitation of the detector, which basically means of up to 2 megagray of absorbed dose in the forward part of the detectors. So we are really talking here, you can see the scale of the radiation that the part of the detector have to withstand. We are really in the megarad kind of conditions. The other thing which I will not talk about, but we'll hear more from Piero Giorgio later, is basically that you have an extremely high data rate. So basically you will have enormous challenges also on the computing side. To give you an idea, the data rate at high luminosity LHC will basically provoke a flow of data at the front end of the detectors, which is several times the whole internet of Earth today. So it gives the scale. Now, when you look at what is needed in order for our detectors in order to cope with this, you can see that we basically have to upgrade every part of the detector. In particular, we'll have to replace all of the electronics of every detector, but they're going to be part of the detector, in particular is the tracker, the central part, and for us the forward part, which will need to be replaced because by the start of the high luminosity LHC, the detectors will have reached the end of their lives in terms of performance due to the radiation they've been exposed to. There's going to be a major challenge as well at the level of the trigger and the data acquisition, which I will not have the time to go through, but you can see that today we are basically writing out something like 1 to 2 kilohertz of data. We will have to push that amount to 4 or 5 times that in order to be able to exploit correctly the physics that the accelerator is going to give us. And we are also introducing new concepts, which I will talk about in terms of timing. When you look at the Atlas detector upgrade, you can see that there is similar concerns, in particular regarding the electronics. The major difference between the global upgrade of Atlas and the global upgrade of CMS is that we need to replace the forward calorimeter system, while Atlas with the liquid argon will be able to continue to work with the existing detector, albeit upgrading the electronics of it. So the tracker upgrade is basically something which, seen from a distance, would look similar to what we have today. It's still going to be order of 200 square meters of silicon detectors. They're going to be arranged in a different way compared to what is the central tracker of CMS today. But you can see it is going to basically lead to a number of channels which is roughly 2 times what we have today. We need to basically go to much smaller diodes for our silicon detector in order to cope with the enormous multiplicity of the events which are coming in. But and we are basically profiting from advances in technology when it comes to the cooling which we are going to use for our detectors, because we are going to use CO2 cooling instead of using more conventional means of cooling the detector. And you can see that that is going to benefit the amount of material and, if you like, the effect of radiations on our detectors in the components of the detector, and especially in the part of the detector which is sitting in front of the calorimeter, so that which was effectively reducing the performance of what we could achieve for detecting electrons and photons. And you can see that basically we achieve almost a reduction by more than a factor of 2 of the material in front of the calorimeters. Now, similar thing is for Atlas. For Atlas, it's going to be a major change of paradigm in the sense that they're going to do something which is more similar to CMS, in the sense that their tracker is going to be full silicon from the moment after the upgrade for high luminosity LHC. And they have as well a similar concept to CMS, in the sense that they're going to extend the coverage to much smaller angle in order to exploit better the physics in the forward region of the detector, which in turn is going to give us advantages when it comes to understanding better the features of the standard model, especially when it comes to WW scattering, for example. Some of the closure tests for the standard model. But the novel feature in CMS, which basically explains as well the difference in the way we set the silicon layers between CMS and Atlas, is basically that we are going to have tracking at the first level trigger over the full range of the detector, because basically all of our new silicon modules are going to be doublets, which will be able to select, if you like, particles of the curvature of the particles which are going through the detector, such that we can at very early in the data flow chain being able to tell whether the track which is going through the detector exceeds a certain momentum. That basically will have major advantages when it comes to the resolution, for example, and the effect on the trigger rate for muons, for example, and actually the sharpness of the definition on our selections of muons. You can see it here for a typical threshold for selections of muon, which is like, for example, at the level 1 for a 20 GeV muon, and you can see the major reduction in rate, which is going to be achieved by having this at the first level. But the big challenge for CMS is the replacement of the forward colorimeter. The forward colorimeter, which today is has an electromagnetic part which is made out of like tungstate crystals, and an electronic part which is made out of brass and scintillator planes, will basically be dead by the end, would be dead after the first run at high luminosity LHC. So we need to use the time between now and the long shutdown to develop a new detector and install it during long shutdown ahead of the start of high luminosity LHC. And after a long discussion and exploration within the experiment, the experiment has decided to use an idea which had been developed within the linear collider community, which is of using silicon as an active element for the detector. This basically is allowed mostly by the fact that the price of silicon has gone down tremendously from the time when we started using silicon detectors in high energy physics, and so we basically can afford it, but also is because it has been proven that silicon can actually resist to this very high radiation field. And you can see in fact that there's going to be in the new detector sections which are going to be high resolutions, meaning with sampling which is which is very fine, which is the electromagnetic part, and then also an hadronic part, where basically we are using silicon in the hadronic part only where we need it in order to be able to resist radiation. And we go with cheaper scintillator active elements where we can afford to do it, and where basically we are sure that the thing will last until the end of high luminosity LHC. So you can see the design. It's a challenge. It's a challenge because even technologically, here we are talking about 600 square meters of silicon. So just the silicon foundry are put under pressure, because I mean, between Atlas has 200 square meters, tracker, we have 200 square meters tracker, and then we have 600 square meters of silicon. So all together we are talking about 1,000 square meters of silicon. In fact, we are now sure that we are going to manage to do it, but it is putting stress on the producer, which is unique. Now, the fact of one constraint on the performance of the colorimeter, which basically means that we would like to be able to use minimum ionizing particle to calibrate the detector, like we do with usually with calorimeters, makes it such that we get, as a side benefit, an incredible resolution in the sampling of our showers. We will get 39 samplings of basically 1 centimeter square size of the development of the shower. That basically will allow us to exploit this in terms of seeing a lot more details on how showers develop within our calorimeter. The challenges is on the software, and this is something which is being tackled now. We have enormous amount of people working on it now. A lot of the young people in CMS are working in this aspect. Also on the trigger side, in order to be able not to be swamped by the amount of information which is coming out. There are other challenges here. More on top of the 600 square meters of silicon, the 500 square meters of scintillator tiles, is that in order to be able to guarantee that this will survive until the end of high luminosity LHC, we have to cool down the silicon. As you know, we have to work at low temperature, and so one of the challenges is to keep this 400 tons object at minus 40 degrees with electronics installed onto the detector, which dissipates 150 kilowatt. All of this is basically being tackled by our engineers, and we are now sure that we are going to manage to deal with these challenges. I think that one of the challenges as well, which I said, is basically to exploit the huge amount of information, and this has become really a playing ground for all of the young people which are interested in deep learning and artificial intelligence. Now, you also have another benefit, is that silicon is very quick, and so we can exploit the timing as well of this, of the ionization which is detected at the various silicon planes, and adding together, averaging together the information on timing of the many layers which are concerned with the developing shower, we basically can achieve at the beginning of exploitation order of 30 to 40 picosecond resolution, and at the end of exploitation order of 50 picosecond resolution. So when you do that, you basically get an additional handle on handling the huge pileup, in the sense that when you identify which is the vertex which contains the kind of physics you want to explore, you will be able to clean up a lot of the information in the calorimeter, and here it gives you this gives you an idea of what this cleanup, based just on the timing, will give you in terms of, this is the raw data of what will be seen by the detector for an event where there's been vector boson fusion productions of two jets, and this is what happens after you apply a cut on the timing, and it becomes much clearer. In fact, the whole idea of all of the things which we are trying to implement now is to be able to have handles which allow us to make that a 200 pileup event is similar to what we have today, because we know that if you go back to the condition which we have today, we are able to have a performance on the physics side which basically will allow us to achieve what Gigi was showing you. The other thing which we are using this upgrade for, which is also along the lines of allowing us to handle, and giving us an additional handle toward the pileup, is basically the timing. We are adding a fourth dimensions to the reconstruction of our event, because we are going to cover the whole space of the detector with a plane in the barrel made out of crystals, and in the end caps made out of byfast silicon detectors, which is going to give us a timing on individual particles which is aiming to be between 30 and 50 picosecond resolution. With this, we will be able to basically assign a timing to every particle which comes out of the interaction point, and in this case, you can see that when you look at how the interactions, how the luminosity area in CMS looks like, it is basically we have two bunches of protons which are colliding, and the two bunches have an extension in RMS of 5 centimeters in Z and 180 picoseconds in time. And you can see that you can have situations which are highlighted, for example, by the circles, where without the timing information, you would be confusing the particles which are coming from two vertices which are actually separated. When you add the timing information, you basically are able to define which particles are coming from one vertex or the other, and so to clean up further the information and be able to reduce the confusion which is coming from the additional proton-proton collisions. And I am done here. I'm ready to deal with answers. As I said, one of the challenges which is on the computing side, I think, is going to be more tackled from Pier Giorgio, who's going to look at